Yesterday we started talking about pointers and dynamic arrays. Well, I mean, you are supposed to know what pointers and how to use them with the dynamic arrays using malloc and free. We are going to see how we are doing the same thing with C++. Again, this chapter will be mostly about C++ and C, not much object-oriented rules, but as always, since this is C++, we will end up writing a number of classes, and inside those classes we will have pointers. So this is about, maybe this chapter is about, you may view it as like how to use pointers with classes, because with the pointers and dynamic stuff, you have to be careful because your variables are not automatic anymore. You have to construct your variables yourself, and you have to delete them yourself, and etc. So let's see one simple example here. This one is, okay. Let's say I have this code. What did we say before? V1 and V2 are two simple integers. They can hold integer values in them. P1 and P2 are two simple integer pointers or integer addresses. They can hold integer addresses in them. This is the definition. When I write this line and when I execute it, okay, this is what I get after executing these lines. V1, okay, V1 gets the value of 88. V2 gets the value of 53. P1 gets the value of address of V1, and P2 gets the value of address of V2. If I do this, let me take this to nearby place so that we can see it while I am working on it, okay? If I do this, this is what happens in my memory, okay? V1 is this position. Its initial value is 88. V2 is at this position. Its initial value is 53. And the compiler, the code that it produced, somehow assigned V1's position to this address. It is 0x2A01, an hexadecimal number. And V2 is placed at this position. We don't care where they live, okay? It is up to the compiler. It is up to the environment where my variables live. I don't care. And other than the pointers, actually, we don't talk about the addresses much, but the pointers are about addresses. We say that when P1 gets assigned a value, we say that V1 will be assigned a value of address, and this address is, how come I can't, okay. That address is the address of variable V1, okay. P1 can hold an address, and I am going to assign the address of V1 to P1. This is what I do. There are two operator executions here. One of them is this ampersand sign, which is, if I use it with the an integer, it gives me the address of that integer. Address of that integer is this, okay. Let me get rid of these. So P1 is doing this. Address of this integer is pointing to that one. I just put 2A01 to P1, and I put 2B A0 to, okay, P2. That's it. Basically, 1, 2, 3, 4 assignments. That's it. Okay. For the assignments, I can use only integers for the integer variables, and I can use only addresses for the pointers, integer pointers. This is as simple as this. Since we are talking about the addresses, I mean, when we talk about V1, as I said before, I don't care where it lives. It just value is an integer. But with the pointers, situation is a little bit different, not complicated, but different. We say that P1 can hold a value, and that value is an address of another integer. Okay, so P1 by itself is not that meaningful. It has to be assigned a value of an integer, and so it has to live with that integer. That's why you may think that it is a little bit more involved than just handling an integer. So P1 by itself doesn't do much. It is just an address variable. So I need to put an address. So where do I get the address? I cannot put a random address in it. I need to put a meaningful address, and this is the meaningful address here. Okay. Then when I do stuff, like this, let's say I am going to increment v1 by 2. Of course, compiler knows where the variable v1 lives. It goes there, it finds it, and it says that it's 88. I am going to add 2 to it, so it becomes 90 now. Okay, so I can do that. How about if I do the same thing with P1? If I say P1 plus assignment 2, the meaning of this plus assignment is very different than this plus assignment. This means that add 2 integer size values to P1. Okay, so what am I going to do is going to, let me do this P2, not P1. Okay, P2. So compiler says that, okay, where is P2? P2 is here. What is its initial value? Its value. It is 2b_a0. I am going to get this value and I am going to add 2 to it. But meaning for a pointer to add 2 means that what is the pointer type? It is integer. So I am going to add 2 integer sizes to it. If I add 2 integer sizes, assuming that my integers are 4 bytes, then it's going to be 2b_a8, right? So this is going to be 8. So it is not pointing to this location anymore. It is pointing to some other location in the memory. Where is it pointing? I don't know. It is pointing to some place. It might belong to me, okay? Okay, it might belong to me, or it is somewhere else. But whatever it is, I am not doing a very, very good thing here, okay? I am pointing to some place that is either garbage or that doesn't belong to me. I didn't do a good thing, okay? But these are your variables. Like any value I can put in these v1 and v2. I can put any values in these p1 and p2 too. I can do whatever I want. So I am, as a C programmer, I am responsible for making sure that I am pointing to correct places, meaningful places. In this case, it is not pointing to a meaningful place. So question for you. Is doing this immediately will cause a crash, program crash? I am pointing to somewhere that that doesn't belong to me. Let's say this position doesn't belong to me. Okay. Does this cause a crash?
Depends on the place.
What do you mean?
Runtime term.
What do you mean depends on the place? It's a place that doesn't belong to me, okay? It's a place that belongs to the operating system, let's say. So is this a segmentation fault? Adding 2 to this P2?
But if it's just a garbage value, I think.
Well, I'm saying that it is not garbage. It's a place that belongs to the operating system, not myself. So is that a segmentation fault? You know the meaning, right? You're supposed to say no, and I'm going to say why. This is not a segmentation fault, no. Why?
Not access valid memory or valid spaces.
Say it again.
Not access valid spaces.
So it is not a segmentation fault, I am saying. It is not a valid space. So why it is not a segmentation fault then? P2 plus assignment 2 is not a segmentation fault. It doesn't depend on, I mean, you might say that from time to time you are going to get a segmentation fault. No. You will never get a segmentation fault out of this P2 plus assignment 2. Even P2 plus assignment 1 million will not give you any will not give you any segmentation faults. Yes?
I think I tried this before and I saw some error called bus error. I'm not sure.
This will not cause any errors. Your program will continue running. Yes? I am the professor here. I'm asking the question. Why? Yeah, that's a good exam question. Why? Yes?
I think when you try to reach this memory, it will give an error.
Exactly. I didn't reach anywhere. I am just pointing to it. Okay. Is this a runtime error 90? I am assigning a value of 90 to this integer? No. I can put any values that I want in this position, right? It's just a value assignment. How about this? I can put any values that I want, okay, in my variable. Even if it's a garbage value, I can put it. That doesn't mean that I am accessing that location. Accessing a pointer location is this. If you try to access this 71, then that's a no-no. You can't do that, right? You can't do that. Why? Because you don't know where you are accessing. From time to time, this will modify a garbage position. This will modify some of your useful variables. This will sometimes try to modify operating system's memory location. Okay, it depends on your configuration and etc. So this is the bad line that will cause the segmentation fault. Not one, not this one. Okay, how about this one? Integer pointer P7 gets the value of null. What is null? 0. Address number 0 doesn't belong to me, okay? It belongs to the operating system. It is always an invalid place. Is this a compiler error or is this a runtime error? We keep doing this, right, all the time. This becomes a problem when you do this, okay? Or this becomes a problem when you do this, okay? Show me what is at address number 0. So you can't do that because address number 0 is out of your reach. So this is a problem. This is not even, in fact, this is a useful line, right? We keep writing this all the time. Okay, so try to understand what a pointer is. Pointer is, don't think like they are complicated stuff. It is simple. It is as simple as it's a variable. It can hold any value that it wants. Okay, it is how you use it. The important thing is, okay, you can put, if you like, garbage values in it, but as soon as you use that garbage value to access that location, it becomes a problem. Yes.
What's the difference between segmentation fault and bus error?
I don't know what bus error is, so I am not going to. Well, I mean, segmentation fault, usually those are architecture dependent stuff. Some processors use this memory architecture that is defined by segments. Some of them, they don't use the segments at all. They use pages and etc. So the operating system, for example, that segmentation fault is not a C programming error, okay, C programming language error. It's an operating system error, okay? So usually you are giving your segment and you are not supposed to reach out of your segment. If you reach, you'll get a segmentation error. And bus error, maybe you are, why are you guys so late? 46? Did everybody sign their names? Let me do the attendance first, because if I don't do the attendance, because I know there are some people who are, because yesterday I forget about it. If I don't do the attendance 2 days in a row, in the third day, definitely there will be at least. This is how we work actually. Our Turkish culture is always try to fool the authority. Even though we can do the right thing, we should always try to Run the red light. Okay, you were asking a question? Ask it.
Yes. When we say any pointer variable, say plus assignment 2, for example, is it increments address variable as 2 or size of int times 2? Size of that pointer variable.
What did we do here? It was A0, right? Why did we write 8 instead of 0?
When we say plus assignment 2, is it increment as 2 or 2 times?
What was the value here before? 2b A0, right? Why is it 2b A8 now? Because we incremented it by 8. 8 is 2 integer values.
Can I ask you a question?
Just a minute, let me get this assignment first, or the attendance first. Is Kamil here? Kamil Duru. Veysel Cemaloğlu. Veysel. Berke Yılmaz. Diyar. Hasan Karakuş. Çağrı Yıldız. Today is first, right? Furkan. You have no, you are not fast enough, Furkan. Our record is 4 seconds, 6 seconds. Okay. So it looks like 158 and almost 90 people. Okay, good. So what's your question?
If we do not assign a value to a pointer, we will not get segmentation fault, right? If in order to get it, we have to assign.
Are we getting any segmentation faults here?
No, not because of null. Because of
Well, a null is no different than junk value. Null is definitely a place that you should not access. It's definitely, okay? So if you're not getting a segmentation fault for this one, okay, you are not going to get a segmentation fault for a junk value. I mean, you cannot assign any value that is worse than null in terms of accessing. This is definitely a segmentation fault, okay? This might be a segmentation fault, but this is definitely a segmentation fault, okay? So all I am saying is that this is as simple as an integer assignment, okay? This is as simple as incrementing the value of some variable in the memory, okay? When maybe it is our fault that we are showing these arrows as like, as soon as I put a value in here, this one points to that location. No, it doesn't. I mean, these arrows are our interpretation. This is just a value, and this value becomes meaningful when you say that reference P2, that reference P1. Yes?
If we make pointers constant, can we change the value that it points at?
That's a good question. You know what that's a good question means? I have a slide for that. That's what good question means. Excellent question means that's a chapter name. Where is my, since you asked that, I am going to, where did I put that? It's bad. Yeah, here it is. Okay. You can declare an integer pointer in 4 ways. You can say, here's an integer pointer, non-constant integer pointer, and whatever it is pointing to, I can modify it. What does this mean, P2? What is P2? P2 is an integer pointer, but you can't, what? You can change the value it is pointing to, right? You can't change the value it is pointing to. This one is integer pointer constant P3. P3 is an integer pointer. After you assign an initial value to it, you can't change the value of P3. But using the reference P3, you may change any value that you like, okay? And this one, both of them are not possible. So let's look at this. So P1, P2, P3, and P4, okay? When you do P++ for the P1, it will work. I can change the value of P1, it's just a variable. For P2, I can do that too because I am modifying the value of P2. But 3 and 4, P3 is a constant, P4 is a constant. You can't change them, okay? So the second one, why is this so big? Let me make this a little bit smaller. Didn't work. Let me try to make it a little bit. Does it work? No, it did not work. Anyways, I think I make. Does this work? Hey. I will be very careful when I do this. It should work now. Okay, so this is better, I guess. Yeah. Okay, so P++ will be good for P1 and P2, but bad for P3 and P4. The reference P gets the value of 2. What it means? I am not changing the pointer, okay? I am changing the position that the pointer is pointing to. So this one is okay because it's the least restrictive one. I can modify it. This one is bad. Why? Because I promised that I am not going to modify that P2 is pointing, the position that P2 is pointing to. Okay, so this is bad. This one is okay. Why? Because only P3 is constant. It is not the value that is pointing to constant. So this is okay. Of course, for this one, it is bad. Okay. How about this one? C out. Okay. The reference P. All of them are okay because I am not modifying anybody. Neither the position nor neither the address nor the integer that I am pointing to. How about this one? How about this one? Well, I guess this is the same as this one, right? I am modifying the value of P. Okay? So this is, I guess this is the answer to your question. Okay? So if you put const in front of this integer pointer, that means that you are making the integer constant. But if you put this constant in front of this, the P, the pointer itself, the pointer itself is constant. Okay? The pointer itself is constant. Good? And our array declarations, when you say, I have an integer array, A10, okay? It means you have an integer pointer, but it's a constant pointer. And its initial value is someplace in the memory that will show 10 integers. Okay? So, so let me go back to the beginning of the slides. Where are they? Okay, we talked about this. So let's go back to our example codes, okay? Before that, maybe I should just repeat what the book says. Pointer is an address. Address is an integer, right? This is as simple as an integer. And in C++, we don't mix addresses and pointers together. They are different things. I mean, this, okay? Usually, my integers are 4 bytes. My addresses are 4 bytes too, okay? They occupy the same amount of space. They occupy the same amount of space. They have the same size. So why can't we assign this integer to this pointer? And if you like in C, yes, you can do that, but in C++, we don't do it that way, okay? We keep our integer pointers different from integers, or double pointers different from integers, etc. Okay, we talked about that. Okay, in terminology, we talk about pointing then addresses, etc. This is just a way of visualizing it. Of course, in memory, you don't have any like arrows like that, right? Okay, we interpret this number as this one is pointing to this address. Okay, good. We talked about this already. Yeah. The reference operator. Okay, the reference operator is an operator that will work on pointers. It will not work on integers. Okay, in this case, integer, there are 2 integers and there are 2 integer pointers. This will work. This is not a compiler error, but this is a compiler error. This is a compiler error. This is okay. So it's like unary star operator. Okay, there is a binary star operator, there is a unary star operator, there is a unary star operator. Good. Okay, and this is okay. This is something that we keep doing all the time. Let's draw the memory. Let's draw the memory. At the beginning, I have this v1. v1 is 0, and let's say its address is 0x2ba0. Okay, and p1 is somewhere in the memory. Let's say its memory position is 0x2bf0. This guy says that get the address of v1 and put it in p1, 0x2ba0. Okay, that's what I did. Question for you. If I like to put this address to some other variable, what should I do? I am going to have another variable, and this variable will hold this value, 0x2bf0. What kind of variable should it be? What? Why are you whispering?
Pointer of pointer.
Okay, I am going to make you sit at the back of the slide class. Whatever you are saying, only these 2 guys and me can hear it, okay? Say it louder. Pointer of a pointer. So what do you mean? So what do you mean? What am I going to write? Let's say its name is pp1. So what is the type of pp1?
Integer pointer.
Integer pointer. Let's forget about this part. pp1 is a pointer, so yeah. It's not an integer pointer because it is not going to hold the address of an integer. It's going to hold the address of an integer pointer. Okay? So I am going to say take the address of p1 and assign it to this value. And for some reason, some people, when I write this, for them this expression, this syntax is somehow okay scary. I don't know why. I mean, just a regular pointer, it's a pointer. It could be a double pointer, it could be a money pointer, it could be a bank account pointer, or it could be an integer pointer. I mean, does it matter what I write in here? It's a type, right? Integer pointer. I mean, if you are scared, then maybe you can do this. Make a new type def. Okay, My new type definition name is int pointer. Then you can say maybe integer pointer. But I mean, syntax-wise, it is exactly the same thing. Okay, I defined a new type def from C, remember? I can do that, but I don't prefer this kind of a notation. This is much cleaner, okay? Integer pointer pp1 gets the value of p1. Okay? So this is pp1. Where are we going to use this pp1? Okay, integer pointer. Where are we going to use them? In C, if we are going to do simulated call by reference on a pointer, then I have to use it this way. Okay, if you are going to use simulated call by reference on an integer, then an integer pointer is enough. But if you are going to do simulated call by reference on an integer pointer, then you have to use this one. So it is useful too. So this is not just for an exercise. This will be used in many places. Address of operator. Remember what I said about the address of operator. It is valid. It is one of the few things that is available on my favorite class, class A. Remember this one? So objects of, this is my favorite class definition, and this is my favorite variable. Okay? So this is possible. That's why we have the semicolon here, right? A is an object of, this A is an object of class A, capital A. So I call the no parameter constructor here, and address of operator will work here. So I can say A star AP, A pointer gets this value. So this address operator works. Okay, address of operator works. Don't get confused about this. Okay, when I say star AP, is star implemented for this class? No, it is implemented for the pointers of that class, not for that class, but pointers of that class. So AP is not a, hold on. Efendim Ali Bey.
Hocam günaydın.
Günaydın.
Hocam bugün 10.30'daki toplantısından Sarı hocamla görüştük de 11 almayı planımız var mıdır?
Olur ha, tabii ki.
Sağ olun hocam. 11 olarak. Biz de Sarı hocamızın çok yarım saat onu uzatması gerekiyor.
Oldu. Görüşmek üzere.
Görüşürüz hocam. Sağ olun.
So the address operator will work for any class, okay? And even though you can overload it, it is often suggested that you don't overload this address operator, address of operator. Okay, pointer assignments. I mean, these are as simple as integer assignments or double assignments. That will work. So we talked about those. Okay, if we have two pointers, they are pointing to two different things. Okay, when we do this assignment, then picture becomes this. Okay, so both P1 and P2 are pointing to the same variable. Okay, but if you do this is a pointer assignment, this is an integer assignment. Okay, when you do this, this 9 is assigned to this location. Okay, these are kind of repetitions of what you had been doing. Then let's talk about this new operator. Yes.
Can we point to different places?
At the same time?
Yes.
How it's going to happen? I mean, can an integer hold two different integer values?
No.
Integer I7. Can it hold both 7 and 17?
No.
A pointer is no different than integer, right? It can hold a single value, it's just a variable. Okay, the new operator is what we did with malloc in C. Exactly the same thing, the new operator. Okay, malloc creates some space in heap, and makes it available for you, and that space is available for you until Either you give that space back or your program terminates. It is very different than automatic variables. Okay, what are the automatic variables? Automatic variables are this: integer function f, double d, character c, initial values, let's say b, and then in an if statement, I don't know what it is, then I have an integer k, blah blah, and here is my function ends, return -1. Okay, so this c is an automatic variable. Why? Because it is automatically deleted when the scope ends. For c, the scope is here. Okay, for d, the scope is here. For k, the scope is here. Okay, when the scope ends, okay, that automatic variable will be automatically killed. That's what we like about automatic variables. We make them, we construct them, and we don't think about the rest. We don't say what's going to happen to this variable in the memory. Okay, it will be automatically killed when the scope ends. When this function ends, f, d will be gone, c will be gone, k will be gone. Whatever you define locally, they are all automatic variables. Okay, they are all automatic variables. That's what we like about automatic variables. We don't have to look after them. Okay, we just use them, and whenever we are done, they will go away. That's not the same. Okay, with the dynamically allocated variables, because dynamically allocated variables are constructed in a special memory location, and they continue their existence until you delete them, until you say that I am done with this, or your program terminates. In that case, your whole process's memory will be returned to efendim.
Hocam sizinle görüştükten sonra Hasar hocam tekrar aradı. Dün görüşmüşsünüz herhalde bu konuyla ilgili.
Evet, biraz daha bekleyeceğiz demişti, evet.
Cuma yani o konudan haberim yok. Cuma gününe ancak bazı verileri toparlayabildik
Evet.
gibi bir görüşmeniz oluşmuş. Sizce de uygunsa o zaman bugünkünü iptal edelim. Cuma günü elinizde istediğiniz veriler varken.
Olur, tamam. Hı hı.
Cuma günü sizin de hocamın da uygun olacağı bir saatte bir araya geleceğiz.
Olur, teşekkürler.
Kolay gelsin.
Teşekkürler. So dynamically allocated variables, as I said before, they are not automatic. That's why they are powerful, because you control them. I mean, you say that, give me a dynamically allocated variable. Okay, it says here it is. You keep using it, but you are responsible for deleting it. If you don't delete a dynamically allocated variable, then you are wasting your memory space. And if you keep doing this a lot of times, then you will end up using all of your memory space, and operating system will terminate your process. It will say that you don't have any memory anymore. Yes.
We can point an empty class. So
You do what?
we can point an empty class.
Why not? Didn't I do that here?
So what's size of an empty class?
Oh, well, its size is not 0. The question is this: what is the size of your favorite class A, right? What does? Okay, let me. I like this class because it is so easy to write. Class A. What does this cout size of A will print on the screen? I tell you, it is not 0. If it is 0, then I can't make an array of it, right? I can say I have an array of 100. If it is 0, they will be all in the same place. Or where does this A live? If it is size is 0, where am I going to put that 0, right? So it is not 0. So what do I hold in it? Well, I think it will be, well, why do I like this class? I mean, it looks like it is empty, but it's not empty, right? I know that the default constructor, copy constructor, address of operator, assignment operator, they all work for this one. They are all defined for that one. There are some other stuff that we are going to learn in our inheritance chapter. And in that case, you will see that this is not as empty as it looks. This is a class that contains some information. Okay, so why did you ask? I mean, I'm talking about new operator and you're oh, okay, you thought about when I say new A, what kind of thing is going to make, yeah, okay. So new will work on that one too, and it's not going to give you a zero size location. So let's look at this one. Let's look at this one. How are we going to do it? Let me show you one picture that I shared some time ago with people. This is the structure of your process. Your process is your program running in the memory. Program is something static, okay? You write your program, you compile it, and it sits on the desk, right? That's your program. If you start running your program, that becomes a process, okay? So you need to load that program to your memory, and it starts running, it starts using the CPU and your memory, and your running program is structured like this in the memory. The code is at the bottom. The code is at the bottom. The address 000, remember this is null. You are not supposed to write anything inside your code section. That's why it gives you a segmentation fault. This is your code segment, okay? At the top, you have your heap. Heap is the place where the dynamic variables are stored, okay? Heap is the place where your dynamic variables are stored. And I have the stack. Stack is the local variables or the automatic variables, okay? So you put your new local variables on top of each other stack, and stack grows upwards, heap grows downwards. This is your available space in between. If there is no space here, then you are out of space and your program will be terminated by your operating system. It's a modern operating system. If it's an old operating system or a very small operating system, then your program and your operating system will crash at the same time. Okay, yes?
When we forgot to free any dynamic variable in heap and parameter, is garbage collector free?
What's a garbage collector? I don't know what garbage collector is. In C++, we don't have garbage collectors. Okay? Garbage collectors are for children. This is C. Okay? We look after ourselves. We don't leave any garbage around.
If we leave, it's there, right?
Well, if you leave it there, it is not garbage, obviously. If you keep leaving your garbage around, then your whole memory will be filled up and your program will be terminated. Even if it is not terminated, you write a very small application. It is supposed to do a very simple thing, but it is using gigabytes of memory space.
I'm asking after termination, is it already in heap?
After termination, everything is taken care of by the operating system. We don't think about that. Unless you have a very primitive operating system. Some primitive operating systems, I mean, this is a very complicated operating system, Windows or the Ubuntu. Those are very complicated operating systems, and they are very robust. It is not easy to crash them. It is not easy to modify their internal workings. I mean, if you are a hacker and if you are after it, of course you can do it. But if you are a regular programmer and if it is not your intention to crash your operating system, and it's difficult. What's going on? Okay, it is difficult to crash these kind of operating systems. After your program is done, all of your heap, your stack, and your code will be cleaned up, and it will be a fresh memory for the operating system. Okay, so this is our structure of memory when our program runs. Okay, whenever you use this keyword new or malloc, function malloc, you are using space from that location. Let's look at this example. Okay, again, I am going to draw let's say this is my process. At the bottom, I have my code. Okay, this is address 000. My main function started running. As soon as it started running, it says that I am going to have two integer pointers. This is P1 and this is P2. Remember, this is my, let me do it this way. This is my empty space, or maybe I should print my empty space like this. This is my empty space. This is my stack, and this is my heap. Okay, as soon as my main function started running, P1 and P2, okay, they will be constructed. They will be constructed, and their initial values are garbage. I don't know where they are pointing to. Maybe they are pointing to this location, maybe they are pointing to this location. So whatever they are pointing to, I don't know. Probably, most probably they are 0. They are pointing to 0. They are pointing to some garbage location. But I don't care because I'm not going to use them directly. Okay? So they are pointing to some place. Then it says that P1 gets a value of new integer. New int means that, okay, make an integer in my heap. Okay. By the way, call it no parameter constructor to initialize it. Well, integers no parameter constructor doesn't do anything. It doesn't initialize it. Leave it as junk. Okay. So it created this new integer for me. But remember, this is a nameless integer. It doesn't have a name. Okay. I cannot give any names to the variables that I constructed in my heap. I just make a new one. So how am I going to refer to it? This one says that assign this address to P1. So P1 now, it is not junk anymore. Okay, it's not pointing to junk anymore. It is pointing to this new location that I have constructed using this new keyword. New is a keyword, C++ keyword. Malloc and free are not C keywords. They are like printf and scanf. They are function names. Okay, new is a keyword, C++ keyword. I made the new integer here. It's a new integer. Good. And then still this P2 is not pointing to. Let me draw P2 by, let's say, a red arrow so that we know that it is pointing to somewhere meaningless. And then I am doing this. The reference P1 means that compiler says, see, this one, there are two operators. One is this, the other one is this. This one has a higher precedence than the assignment operator, right? So the reference P1 will be done first. So what does it mean? Okay, get me an L value out of this. So the L value will point to this location. Okay, L value will point to this location. So L value is say that I am here. I am going to put 42 at this location, 42. Okay. So 42 is there. That's good, no problem. So I have total 3 variables. 2 of them are automatic, P1 and P2. One of them is dynamically allocated. It is not automatic. Okay. Then I continue with line 10. Line 10 says that assign P1 to P2. So what is the value of P1? Let's say the value of P1, the same address here, 0x f to b 0. So 0x f to be 0. Compiler knows where this one is, and this one is. Okay. So it says that I am going to assign this value. So that's basically it. I mean, when I do this assignment, line 10, basically you copy this number to this location. You copy this number to this location. So that's what I'm going to do. 0x f to be 0. That's it. Okay. So I did it. Then This red arrow will go away, and this one is pointing to the same location too, both of them. So you might say, well, isn't that confusing? Why are they pointing to the same place? Well, it can happen. I mean, can't I have two integers having the same value? I and j, they are holding the same value of 7, right? It is as simple as that. Okay. So after that, if I print this out, that reference P1, that referencing it is here, okay, 42. This one will print 42 on the screen. This one will print 42 on the screen. Okay. Then if I do this, that reference P2, see, I use this reference as an R value. Now I am using it an L value. The reference P2 gets the value of 53. So this becomes 53. And when I execute exactly the same lines, this time I will get two 53s on my screen. Okay. And then if I continue doing this, Control V, let's do this in here. Okay, so it looks like line 16, I am going to get a new integer. Okay, it's going to look like I am going to get a new integer. How am I going to do that? Okay, assignment will be done later. This operator will be done first, new. Remember my operator precedence table? New and delete are operators. They are unary operators, and their precedence is higher than assignment operator. So new will be done before the assignment operator. So new integer, okay. In the heap, I will get a new integer. Okay, whatever it is. And that address of that integer will be assigned to P1. So P1 is now pointing to this new location, P1. It is not pointing to that location anymore. Let's say this is 0xf to D0. So this is going to be 0xf to D0. Okay, so P1 is pointing to that location now. And when I do this P1 dereference, I put my hand in here and I put an 88, value of 88 in this location. Okay, so I have total of four variables in my memory. Okay, 4 variables in my memory. 2 of them are local automatic variables. 2 of them are dynamically created. Okay, when I print these two, the reference P1, follow the link of P1, it is 88. This will print 88 on the screen, and this will print 53 on the screen. And then when I end my function, this P1 and P2 will be deleted automatically. Those are automatic. But I forgot to delete these two dynamically allocated variables in my heap. So what's going to happen? Operating system will take care of it. But this is a bad program. Why? Because what did I say? Every dynamically allocated variable, you should delete it yourself. I didn't delete them. So the correct thing would have been, okay, after I am done, delete P1, okay. Delete P1 means this. Go to P1, it holds a memory location address, okay. It is here. So I am going to give that location back to the operating system. It is back to you, okay. So deleting P1, so tell me what happens after I do this, delete P1. How does this picture change? What am I going to do with this picture? Am I going to erase this arrow? Am I going to change this value? What am I going to do? Yes?
Delete the content of P1.
How do you delete it? How do you delete?
Erase. We will forget.
Erase it?
Yeah.
So what you don't, your memory locations, they always hold a value. I need to put something in there, right? There is no empty memory location. It's either a garbage value or some meaningful value. In this case, it's a meaningful value, but after I delete it, what happens? After I delete it, so you didn't study pointers at all in your C programming languages? So no surprise that only one people get an AA from C? These are not difficult stuff. These are just regular questions, regular C questions. I hope whoever knows this answer to this question, I hope they are shy. I hope they take care of their shyness in a very short amount of time. But what happens when I free a memory location? Yes?
Maybe if we delete P1 content, the address will be gone and 88 will be
What do you mean address will be gone? What am I gonna, you are the professor, okay? You are going to make a new change. When I do this, delete P1, what am I gonna draw on this picture? Tell me.
P1 address
Yeah.
0xf000 will be gone.
What do you mean gone?
It's just deleted.
We forget it.
So what am I gonna do here?
It's just stack deallocates P1.
So what am I gonna draw in this picture? When you say, okay, P1 is a variable, right? It should hold a value. When you say it is gone, what should it hold now? What? Zero, null. Where did you get that idea? Well, it's a better answer than it is gone. No, it is not zero. Yeah.
I think we will just delete the arrow.
But this value is there. Like why? I mean, this arrow is not. This arrow is for me only. Okay.
No naming.
I will just delete the name P1.
Name.
Name.
I'm going to tell you something. I'm not going to change anything. When you say delete P1, it tells the operating system that this location does not belong to me anymore. Okay, this location does not belong to me anymore. I am not going to use it, I promise. Okay, and operating system says that okay, I am going to use that location for somebody else. Then after that, if you do this, what happens? Just after deleting P1. Say it louder.
Garbage value.
Garbage value. Okay, and most probably that garbage value will be 88. Right?
There is no such thing as P1 after that, right?
There is such thing as P1. Of course, P1 lives here. P1 is not deleted. This location is deleted, okay? This dynamically allocated place is deleted. P1 lives. P1 is automatic. It is not deleted. But whenever I do this, just right after this one, I am doing a bad thing. This is a bad thing, okay? This is a bad thing. This is bad. But you might say that how come this is not bad? The green thing is okay because I did that before I deleting, sorry. The green thing, both of them are okay because I did that before I deleting P1, okay? It is okay. And I did the right thing. I assigned an 88 and this one will print an 88 on the screen. But when I say delete P1, okay, it is saying that I am not going to use this location anymore. I accept that it doesn't belong to me, but I keep pointing to it. As soon as I execute this one, P1 holds a garbage value. What you are saying is right. But garbage value doesn't mean that it becomes 0, it becomes something else. 88 is now for me garbage value. Okay, when I do this, most probably, you will get 88 on the screen. Okay, most probably you will get 88 on the screen. Depending on your operating system, sometimes you might get a crash too, because you will never know what you're gonna get at a position that doesn't belong to you. Okay, it is how the operating systems work. Okay, good. Let's take some break. 10 minutes. After the break, we will continue.
Hocam merhaba. Kusura bakmayın ben devamsızlığı işlemi unuttum da acaba ne kadar imza atabilir miyim?
Yok ya, onu söyledik ya, ders sırasında hatırlatmadım mı ben? Saatinizi falan filan kurun ya, ben artık kağıt tutmuyorum.
Yani o zaman yok mu ya?
Teşekkür hocam, dersteydim, cevap veremedim. Buyurun. Evet. Evet yani vazgeçirmeye çalıştık. Epeyce şikayeti vardı hocanın. Rektöre gittik beraber ama yok, ben ayırıyorum dedi. Evet.
O saatlerde olabilir dedi ya. Ne kadar da gidelim. Güvenlik kartında mı? Gidelim mi? Evet, gidelim. Senin tanıştın mı? Diğeri buraya mı? Bir tane şey var ya, git oraya, orada ben şey yaptım, yeni bir tane çıkarttım. Ben onu severdim. Senden otobüste olsun. Benim otobüste. Ben hiç yaptım mı? O zaman bir bakayım. Ona bakayım. Mideye biraz fazla iyi geldi sabahına. Değil mi yani? Ben kendim Şengül sofrası kurarım sana. Bırak bir şey. Ben deneyeceğim. Bu aldığım ilk günü hatırlıyorum. Siyahlar. Şey var ya içinde kıyafetleri falan koyuyor. İşte renklilerle şeyleri siyahları birlikte yıkadığımda bu da var. Benim niyetim de ama geçmiyor. Pembe olmasaydı elektrolardı. Şunun gibi bir şey. Ekran dışı.
Çoğu programda ne bileyim sürekli yeni gördüğünde falan bir söyleme geliyor. Şöyle insan sonra iyi vardı ama var ya.
Hala gidiyor. Soruluyor da kimse pembe olduğunu bilmiyordu.
Ya senin gel kaçına girsin.
Normalde herkes yapıyor. Ama benim uyanınca
O biraz yapsaydı orada birlikte aynen. Paşam. Yaşın gidecek kadar gidiyorsun. Evet.
Attendance is on. Sign your names in the online form. Okay. let's move on. So the correct behavior, so the correct programming in this case would be to get rid of this one, delete both of them, delete P1 and P2 after we are done with them, okay? So previously, what was the difference between this one and the previous version, where I didn't delete this P1 and P2? Operating system took care of P1 and P2 for me, because operating system cleared everything from the memory, because this whole process is gone, including P1, P2, and these two locations. Okay.
Can I ask
Any
you,
question? Sure.
you said we or anyone can we also assign to deleted pointer variable for the reference pointer one after delete pointer one?
Well, whatever you do after you delete these two, okay, anything you do is wrong. You shouldn't do it.
As is it change in memory even if we make something wrong? I know, but is it going to change in memory?
Well, you are asking something about, well, yes, you can change this position, okay, but that again, it's wrong. You shouldn't do that. Don't do anything at a position that doesn't belong to you, okay? It changes that value, and most of the time, you are not going to realize that you are doing something bad, but from time to time, you will get some weird behavior. From time to time, you are going to get some program crashes, and that's going to be a very tough problem to debug, because I mean, the easiest problem is your compiler error. You can fix it immediately, okay? The next easy thing, you are getting constant crashes. You run your program and it crashes, and you can debug it. The toughest problem is this intermittent crashes. You get a crash from time to time. It crashes sometimes, and the worst thing is you don't get any crashes, but your program works wrong once a year. That would be the worst thing, okay? Because that's a very difficult to find and debug. Okay, good. Okay, let's move on. This was the picture. Okay, so I already drew it. And how about this new operator here? Okay, so I can do this new with my classes, no problem. Okay, here I am saying that in my memory I have a pointer, MC pointer, okay, mcptr, my class pointer, okay, and then in heap I make an object of my class. I don't give it a name, but mcptr points to that one. Let's say this is my money, or well, it doesn't look like money, but let's say it is money. Let's say it is $32.17. Picture will be something like that. Okay, so here I am saying that make an object of my class, but I am going to use, while you are constructing this object of this class, I am going to use the two-parameter constructor. Okay, this my class might have many constructor overloads, no parameter constructor or two-parameter constructor or one-parameter constructor. This is how you do, okay, two-parameter constructor. By the way, this one works too. It looks like integer has a one-parameter constructor. So make me a new integer on the heap and initialize it with 17, and I'm going to point to that location with my pointer n.
Can I ask you a question?
Sure.
If there is callable value, a callable reference, why should I use pointers instead of
The question is, we have call by reference in C++. Why do we need the pointers now? Okay, that's a good question, but I mean, we are not using pointers only for doing the simulated call by reference. We are using pointers for dynamic allocation. How are you gonna implement your string class if you don't have the dynamic allocation? How are you gonna resize your vectors if you don't have the dynamic allocation?
There is resize and
You mean the vector?
yes.
So how did they implement the vector class? Vector class
Yeah, background there is new.
Vector class is a C++ class, and the source code is available and it is written in C++. So wouldn't it be nice to have the capabilities of writing classes like vector class? So if you're going to write a vector class or string class, then you need dynamic allocation. Most of the time you don't need to use it, but whenever you need it, you need dynamic allocation.
So we can't use like integer reference and assign to new integer.
Why can't you?
You said before.
I didn't say anything like that, no. He's asking me, if we have a references, why do we need pointers? I am saying that pointers are not only for call by reference, pointers are for dynamically allocated stuff. Okay, so that's a good question.
New is also dynamic allocated, right?
What?
So new operator also dynamic allocates.
What do you mean also? What? There is no other meaning of new. It is only for dynamic allocation.
I mean, malloc can also do that.
Malloc and free is for C. It's like printf and scanf. We don't use them in C++.
Okay, but so we can use integer reference and assign new type integer.
References and there is an integer I, okay, there is an integer pointer IP address of I, okay, I can do that. And there is this integer reference IRI. All three are okay. Let me initialize this I with 7, okay. All three are okay. This is a pointer, this is a reference. IP and IR are two completely different things, okay. IP and IR are two completely different things. I can do this, give me a, okay, I'm going to assign a new value to I, 17, and I can do this IP gets the value of 37, and I can say IR gets the value of 41. They are all changing the same memory location, but they are very, very different. One of them is an integer. This dereference IP is a pointer manipulation thing. IR is direct reference. IP and IR are two different things. You cannot assign them to each other.
Can we initialize IR with new operator? New memory in heap. Can we assign it to IR?
If IR is a pointer, yes. IR is not a pointer, it's a reference to an integer.
So we can't.
Well, whatever you can do with I, you can do it with IR too. Okay? I is an integer. IR looks like an integer too. It's not a pointer. Okay? Any other questions? Yes?
Can we overload operator new?
Yes, you can, but those kind of overloads are kind of, you are not suggested to use the overload. Sometimes we do this. I overload new, and it says that I am returning a null. Don't make dynamic objects of this class. Okay? Sometimes you do that. Sometimes you do some checking before I do that, but those are very, very rarely done stuff, overloading new. You are allowed to, yes. Since it's an operator, yes, you are allowed to overload it. Good. Okay, so we looked at these, my class, we looked at that one too. Pointers and functions, we already know this. You can send a, this is like sending a reference and returning a reference kind of stuff. Memory management, I already talked about that. Okay, you will have systems programming and operating system courses that will talk about this kind of structure. By the way, this structure is typical for Unix operating systems. For some other operating systems, it may not be valid. It might be different. Okay, C++11 introduced a new pointer constant. Okay, it's called null pointer. Okay, in C we use this define for null. Null is simply integer 0. Okay, that's it. But we said that in C++, we don't like integers being used as addresses. Okay, so they invented this. They say that from now on we are not going to use this define, the definition of 0 for null. There is a new keyword. It's called null ptr. It's a C++ keyword. Okay, it simply means that a null pointer its value is 0. You might think. So why is this a big deal? It's a big deal because I can have these two overloads, right? A function taking an integer and a function taking a integer pointer. If I call this function in C with 0, null, I mean 0 means null address, 0 means integer 0. Which one am I going to call in C++? So they said that we don't use 0 as null, we use null ptr as null value. So when you call this function with null ptr, it definitely will call this overload. Okay, from now on, you are not going to use this null definition. Okay.
Can I show you code example that question I asked for from my phone?
Maybe later after the class. Okay. So C++11 resolved this problem by introducing a new constant null ptr. Null ptr is not an integer. It is not 0, but you may think it as like 0. And it is not integer. It's null pointer. It's a special value. It just says that this pointer is not a valid pointer. Don't use it. Okay. So we use it to show that I initialize this pointer with null pointer. It's not pointing to anywhere. Okay. If you use it, if you dereference it, you will get a crash. Definitely a crash. Okay. So that's one thing. The other thing is when you do this new, it returns you a pointer, right? New int. By the way, remember when we look at the first, where did it go? Okay. Yeah. Remember when we said that malloc and new are kind of almost the same thing. But of course, there are many differences. The main difference is this. When I say new money 100, give me an array of money objects, 100 of them, and call the constructor 100 times for each. Okay, for each of them, call the constructor, no parameter constructor. That will make 100 constructor calls. With the malloc, we don't do that. We say that allocate me space for 100 money objects. That's the meaning of it. So this one both allocates the space, also constructs 100 money objects. So this is way different than this one. This one knows that it is returning a money pointer. This one doesn't know. It returns a void pointer. Okay? So those are some of the very, very big differences between what was my slide number? I forgot my slide number. Okay, yeah. Okay. So this one definitely, after the null pointer, where did I go? Yeah, new success. It looks like I repeated this slide. Okay. this new success, I say that this is definitely return me a pointer, but it's going to return me an integer pointer because this new operator knows that it is working on an integer class, okay? So pointer could be a null. If it is null, then that means that I couldn't get the memory that I needed, okay? So I should check this. If it is null, then insufficient memory and I exit. But this doesn't work all the time. For older compilers, that's the behavior. For the newer compilers, okay, for the newer compilers, if new fails, then your program will be terminated, or it throws an exception and you can catch the exception. You don't know how to handle the exceptions. For now, we are going to do this. If this new fails, I should check if it is null pointer. If it is null pointer, then what are you going to do if there is no such memory is available? Usually we terminate our program voluntarily. We say that I can't continue anymore. Okay? So checking the new success should be done this way. Okay, we talked about that. And free store the heap size. Well, heap is large, but it is not infinitely large. It is finite, and you should be careful. You should always delete your unused spaces. Deletion of your automatic variables are done automatically. That's why we were not that careful about this. Now we have to be very careful about this, because whenever you make an object with a new operator, then you need to delete it, and delete is the operator for that. Okay. So again, the same structure. My code, my stack, and my heap at the top, and this is the place. This is the place empty. Okay. So stack grows upwards, heap grows downwards. Okay. If I am out of this space, the empty space, then my operating system will tell me that I am out of space and it will terminate. Okay, good. So whenever you are done with the dynamically allocated stuff, you are supposed to delete it. Of course, when you do such a thing, for example, I have an integer k, an integer pointer, let's say IP, etc. Then in my program, I did something very stupid like new, let's say, money. That's what I did, okay? That's what I said. New money, $10.20. That's it. And I didn't assign this to anywhere, okay? So basically, this will construct a money object on my heap. It will return a pointer to that constructed space. Since I did not save that location, there is no way that I can delete it now, okay? There is no way that I can delete it now. This is definitely a big problem. We call this problem a leaked memory leak. Memory leak. Why it is leaked? Because I don't have a handle to refer to that memory location. There is no way that I can delete it. There is no way that I can return that memory back to the operating system. So it stays like that in the memory. If I keep doing this, in a loop, okay, in a for loop, keep doing this. You make new money object in a for loop, in an infinite loop. In less than a second, you will fill up all of your memory and your program will be terminated. So basically, you are just making new money objects and you are not deleting them. This is the worst case for memory leak. Worst case for memory leak. Okay.
When your program terminates, or is late?
Well, your program will be automatically terminated by the operating system, and operating system will take the whole thing. Any questions? Yes.
Have non-PTR type? Not PTR.
Null PTR? It's not a type, it's a constant.
We want to some variable for keep the null PTR.
Null PTR is a constant pointer and it is defined for all kinds of types. It is not defined in any libraries. It's part of the. So you are saying that it's kind of a special thing. How does it work? What's its type? Okay, its type is for any class. It is defined including the integers and doubles and money and etc. It is always a pointer. Its value is fixed. Its value is 0. The address number 0. Okay. So if you are, wondering, how can I make a constant like null PTR using C++ code? Well, you can't because it's like for, it's like if, it's part of the language. Okay? That's a good question. So delete works that way. There is this problem of dangling pointers. Remember this one? Okay, remember this one? When I say, get rid of this one. Okay. Okay, this is, let's say I have this integer I, whatever, I did many things in here. Okay, and I have this pointer p. Okay, I deleted it. Let's say I had this p somewhere, new integer, something like that. Maybe this is an integer pointer. After I delete p, what happens? Remember I asked that question. This p is not modified. It is pointing to somewhere that doesn't belong to me. That's called a dangling pointer. Okay, that's called a dangling pointer. Okay, to prevent any dangling pointer means it is pointing to some place that doesn't belong to me. So dangling pointers and memory leaks are kind of, both of them are bad, but they are kind of opposite of each other. With the memory leak, I have memory allocated, but I have no way of accessing it. That's a leak. Dangling pointer is I have a pointer, it is pointing to somewhere that doesn't belong to me. Okay, and both of them are equally bad. Dangling pointers will usually cause segmentation faults, nonsensical behavior. Okay, that's the dangling pointers. Memory leaks, they will not usually cause any weird behavior, but they will keep eating your memory more and more when you run your program. It will keep eating your memory every time you do a memory leak. After a while, you will be out of memory and your program will be terminated, or your computer will be very, very slow because you are using too much memory. Does anybody know why our computers get slow when we use too much memory? Memory and CPU are two different things, right? If I use too much memory, why my programs are getting slow? My CPU is there. Yes?
Fragmentation?
What?
Memory fragmentation.
What is memory fragmentation?
Writes and deletes.
No, it's not. No. Yes?
In order to do some execution, it looks a wider segment of memory, so it takes more time.
Well, memory is memory, right? Every time, trying to access a small amount of memory and large amount of memory is the same thing. You are just accessing your memory. You know how many programs I am running on this computer right now? At least 100 different programs. Okay, and if I try to load all of them at once in my memory, I think I have 8 gigabytes of memory. I will need at least 500 gigabytes of memory to load all of them at once. So operating system never loads all of your program at once. Whenever it is needed, it loads it. When we try to use too much memory, it has to write all of those processes back to disk, and your program is too large, so it has to keep some of your program on the disk. Loading data from the disk, writing to the disk takes lots of time. So that's what is taking so much time. So it gets slower and slower. So when you do the memory leak, I mean, you might say that I have lots of memory. Why does it matter? I mean, instead of using 1 gigabyte of memory, I am going to use 2 gigabytes. No, when you do the memory leak, it kind of gets out of hand, out of control, and you will end up using 1 terabyte of memory, and 1 terabyte of memory will make your computer a lot slower. Okay, so both dangling pointers and memory leaks are bad. They are kind of opposite each other. Okay. Dynamic variables and automatic variables, we talked about them. Let's look at this program, small program. Okay. I have this simple function C. Okay. It takes a character C as a local variable D, and there is an if statement, there is an integer K, and there is a money M. And at the end, I make an integer. Okay, I make an integer. So as I said before, this double D lives at the scope. This integer K lives at the scope, and this money M will live at the scope. This integer PT, okay, will live even after my function f ends. If nobody deletes this one, it will cause a memory leak. That's what we said. It looks like this function f, every time I call this function f, it will make a new integer. And since nobody is deleting it, okay, it will cause a memory leak all the time. 1 by 1, 4 byte, 4 byte, it will eat your heap because you are not deleting them. No problem with the double D, integer K, money M, or character C, because they are automatic. They are all automatically deleted. We already repeated these. So that's the difference between dynamic variables, which are dynamically allocated variables, and the local variables, or automatic variables. I mean, most of the time, of course, you should prefer using local variables. They are nice. We don't have to think about them being deleted, causing. With local variables, there is no way you can get segmentation faults. With local variables, there is no way you can get dangling pointers or the memory leaks and etc. But they are not as powerful as dynamically allocated variables. Okay, with the dynamically allocated variables, your program size gets larger and smaller depending on your needs. With the locals, it is a little bit different story. Okay, I'm going to skip this one. Call by value, call by reference. Okay, well, what did we say? In C, we don't have call by reference at all. We have simulated call by reference, and this is what we do. In C, all we have is call by value. I send an integer to this f, it is copied. I send an integer pointer to this g, it is copied. So the integer pointer value is copied. Not the integer, but the integer pointer value is copied. So it is called by value all the time. And we talked about those. I will skip this one. Sneaky. It is not sneaky, actually. It does something right. Dynamic arrays. Let's talk about them. In C, okay, you are not allowed to say things like this. I have this function f. It takes a k. Okay, I am going to make a double array, double D array and k. No, don't do this. Okay, you cannot by rule. Okay, you cannot create a dynamic array on your heap. This value has to be fixed. You might say that I tried it and it works and etc. No, the standard C say that don't do this. Okay, if you are going to make such an array of size k, that k has to be constant. Either you are going to put 100 in here, or you define a constant integer and assign a value to it. Compiler needs to know the size of the array. Okay, so how are you gonna do that? If you need to do such an array, what are you gonna do is you will say, I have a double pointer dA, and this dA will point to a double array of size k. Okay, so this one will be created. Okay, this one of size k, double array, will be created on the heap. Okay, k number of constructors will be called on this array, and that array will be pointed by dA now. After that, I can access the elements of dA like this. Okay, so this is how you do that. But since this is not automatic, I need to delete this. After I am done, I need to delete this array by using the delete operator. By the way, we delete our arrays like this. You are saying that I am not just a compiler doesn't know that this DA is pointing to a single double or a double array, right? Compiler doesn't know this. By looking at this, it's simple double pointer. Does it point to a single double or an array? Okay, you are saying that you are deleting an array. It is not a single double. Okay, that's the notation. That's the notation. That's why I was trying to be a little bit careful at the beginning of the lecture. Remember this. We should not do it this way. When you say money MP new 100, you should delete it this way. Okay, so this is how you delete it. If you delete it the other way, okay, if you just delete MP, it will delete only the first element of the array, and the rest will be ignored. Or the behavior is unknown. I don't know what's going to happen. But anyways, both cases is going to be a bad thing. Yes.
How does it know the size of the array?
Well, yeah, that's a good question. I mean, how does it know that? Well, I told that it's an array, but how does it know that? Well, it is the housekeeping information for the heap handling. It is the operating system and the C compiler working together. Yeah, it keeps that size somewhere in the heap. So how does that step? How does the step? Okay, let's talk about that. And since you asked that question, that's a good question. This is our process structure, right? Code. This is your stack grows upwards, and this is your heap. Stack always grows upwards because whenever you make a new function call, all of your new variables are put on top of the stack. When the function ends, you delete them one by one. So it is always last in, first out structure, right? That's the meaning of stack. That's how it works. Heap doesn't work that way because I may create an integer here, okay? Later I create a double there. I can delete this integer before the double. It doesn't work. It doesn't work like the stack. Anywhere in my heap, I can create something and delete something. Okay. So how do we keep this structure? Okay, it is up to the implementation of the heap maintenance code. That's a different word. I am not going to talk much about it. Yes. Yes. I am going to give you 5 tokens for each question. Okay. You are not going to ask more than 5 questions per lecture.
It's not only for me, but for everybody.
So you're asking it for everybody? Thank you. But that still includes 5 tokens. Okay, this is your last question.
Okay. When you say
How come
delays-
nobody's asking any questions? Only he's asking the question.
When you say delays, array index operator pointer,
Yeah.
is it also delays memory reference allocations one by one?
Sure. Yeah. All of those. When I say delete MP money pointer money array, it's going to delete all of these 100 objects one by one.
Values.
What do you mean value? It is many objects.
When in C, we only delete first pointer. It's all we need.
No. Well, in C, you do the exactly same thing too. When you say free AP, okay, it deletes, it frees 100 times size of money memory area. It says that I am not going to use this area anymore. In C++, I know that there is an array of many objects, 100 of them. I am going to delete all of them one by one. What do I mean by deleting them one by one? Well, in C++, actually, when the object dies, okay, it doesn't just die, it does something before it dies, okay? It is called destructor. Remember, we have constructors, right? Constructors are called when the object is first constructed, okay? Those are the constructors, and there is a destructor. Destructors are not destructors, but destructors, okay? Destructor is a special function like constructors. It is called when the object is deleted, okay, or when the object is dying. Before the object is dead, it is taken out of the memory. Its destructor is called. We don't know how to write the destructors yet, but you can write your destructors, and that destructor will be automatically called like the constructors, okay? So when you do this, delete MP, that destructor will be called for each object.
What structure does?
What?
What its structure does?
For remember my empty class, it doesn't do anything. If you implement your destructor, it is up to you what the destructor does. Okay, and we are going to write some destructors because remember, for any new allocation, there has to be a delete. So usually we use our destructors to delete any allocated space. Okay. I guess I am out of my time. People are waiting outside. Tomorrow we will continue our regular lectures. I am not going to do this exercise thing or flipped classroom thing. Okay. I need to finish up this chapter number 10. Okay. Regular class tomorrow morning.